In 6.5, we're looking at geometric sequences. I can find explicit and recursive formulas for geometric sequences. I can translate between recursive and explicit formulas for geometric sequences. And I can construct exponential functions to represent geometric sequences. All right, well, you probably remember from earlier in the year, a sequence is arithmetic if it has a common difference, meaning we are adding or subtracting the same number each time. And you might even make yourself a note that this is a linear function if it is arithmetic, we're adding or subtracting. Geometric, on the other hand, oh, that's what we've been talking about. This is our exponential functions. And that means we have a common ratio. And to find the r, we're going to take the second term and we're going to divide the first term. Kind of like what we did in previous lessons when we wrote the exponential function. So we've got a1, a sub 1 equals the first term or the initial condition, the starting point. R is our common ratio. Again, to find that common ratio, we're going to divide the second term by the first term. And then a sub n minus 1 is the previous term. That's going to come into our recursive formula again. My explicit formula, a sub n equals a1, that first term, times my ratio to the n minus 1. N is the term number I'm looking to find. The recursive formula, again, has two parts. You have to use both parts. You have to say a1 equals my initial condition, and then an equals r times a to the n minus 1. You might also see a sub n minus 1 times r. They mean the same thing. All right, so first thing we need to do is decide if the sequence is arithmetic or geometric. So if something is arithmetic, we're thinking about adding or subtracting. So let's see, let's start subtracting here. 100 minus 125 is negative 25. 80 minus 100 is negative 20. All right, they're not the same, so it is not arithmetic. Let's try geometric. So now we're going to divide. 100 over 125, 80 over 100, and 64 over 80. All right, so we want them to be the same if it's going to be geometric. So let me switch over to Desmos. And we have 100 over 125. And let's make that a fraction. 4/5. Okay, next we had 80 over 100. Oh, 4/5. And then we did 64 over 80. You're probably assuming, and assuming correctly it is, that they all have a ratio of 4/5, which means it's a common ratio. Therefore, it is exponential. Okay, so we're going to make all of these 4/5, 4/5, and 4/5. So a common ratio means it is geometric, which means it would be exponential as we graph it. Geometric. All right, and the next one, let's see. -4 minus 8 is -12. -16 minus -4 is -12. And -28 minus -16 is -12. All right, I have a common difference. Therefore, it is arithmetic. Which would mean that it would be linear if I were to graph it. All right, for the rest of this lesson, we're going to assume everything we have is geometric because that is what we are looking at. We are looking at geometric sequences right now. So we need the recursive formula. That has two pieces, a1 equals, and an equals r times an minus 1, that previous term. So the two things we need are the first term. Well, my first term is 256. And then I need the ratio. To find the ratio, I do the second term, divide by the first term. So 128 divided by 256. And I'm going to drop that in the calculator, get a simplified fraction, which is 1/2. So now I have everything I need. I need a1, a sub 1, which is 256. And then a sub n equals r, my ratio, 1/2, times a sub n minus 1. There is my recursive formula. All right, let's do the same thing for the second example. I need my first term. The first thing in my list, my first term is 5. To find my common ratio, I take the second term, 10, divided by the first term, 5. 10 divided by 5 is 2. Recursive formula says a sub 1 equals 5. A sub n equals ratio 2 times a sub n minus 1. There's my recursive formula again. All right, let's do some explicit formulas. So these are actually the same sequences we had before. So we know our first term was 256, and we know our ratio was 1/2. First term was 5, ratio was 2. It's the same sequence as we had in the previous set of problems. Well, we want the explicit formula, which says an equals a1 times r to the n minus 1. So we need the formula first, so an equals a1, 256, times my ratio, 1/2, to the n minus 1 power. That's my formula. And then we want the 10th term, so now I'm going to plug in 10 in place of n. 256 times 1/2 to the 10 minus 1. And again, as a reminder, you got to put parentheses around that in Desmos. All right, let me switch over to Desmos. Okay, so 256 times 1/2 raised to the power of, and we wanted the 10th term, so 10 minus 1. 0.5, which comes out as a fraction. Hopefully you know this one by memory, 1/2. Man, dropping that into the calculator is certainly easier than dividing by 2 or multiplying by 1/2 10 times. All right, same thing for the second example. A sub n equals first term 5 times my ratio 2 to the n minus 1. And now I want the 9th term, so a sub 9 equals 5 times 2 to the 9 minus 1. And I put that in the calculator, I get 1,280. Again, that works a little faster than multiplying it out and making a whole list of 9 terms. All right, last piece of our success criteria was going back and forth between recursive and explicit formulas. So we're going to do that. Given the recursive formula, find the explicit formula. So we're told the initial condition, a sub 1, is 15. And the recursive formula says a sub n equals 7 times a sub n minus 1. So this 7 is my r. So if we want the explicit formula, we simply have to put it together. A sub n equals first term, a1, times my ratio, 7, to the n minus 1. Done. And last but not least, given the explicit formula, find the recursive. So let's see, my first term, a sub 1, is 8. My ratio, my r, is 2. So the recursive formula again has two parts. A sub 1 equals, well, my first term is 8. A sub n equals ratio, r, 2 times a sub n minus 1. There we go. And that is geometric sequences.